For this video, I want to look at Newton's law of gravitation again, this time concentrating on the idea of weight and the gravitational force that a planet causes on you. So quickly reviewing Newton's law of gravitation, between any two objects with mass, there's an attractive force. The force is proportional to the product of the masses and inversely proportional to the square of the distance between the centers of the objects. And in equation form, it looks like this. That capital G is the universal gravitational constant. It's good pretty much everywhere in the universe. M1 and M2 are the two masses, and they're multiplied together. That's what the product of the masses means. And then divided by r squared, which is their separation between the things. This was developed while Newton was in his 20s. It wasn't publicized or published. Nobody knew about his work for about 20 years, and it finally came to light because of an offhand question by Edmund Halley. And Newton wanted to polish up the work a bit, so he had to finish developing calculus and doing some other things before he actually published anything on it. Now, it acts between any two objects with mass: planets, books on a tabletop, people, rats and mice, everything. But it's a weak force. To make it have an appreciable value, you have to have one of the objects has to have a lot of mass. If they both do, that's even better, but in general, you need a lot of mass to be able to have this be an appreciable force. And again, the r stands for the distance between the centers of the objects. It's not necessarily a radius, but sometimes it is. The g is just a proportionality constant that we call the universal gravitational constant. Okay, now let's look at weight. Okay, for an object on the surface of the Earth, like you, standing on the surface, the gravitational force exerted by the planet ends up being this. The F is equal to G times the mass of the Earth times the mass of the object, and we divide by the radius of the Earth squared. Crucial details here. The two objects are the Earth and the object. That object could be you if we're talking about your weight. And the distance that matters, the separation of the objects, is the Earth's radius in this case. The masses that we use here are the mass of the Earth and the mass of the object. Now, the reason that we don't worry about, or we just use the radius of the Earth, is that if you're standing on the surface of the Earth, the distance to the center of the Earth is about 6,370,000 meters. And compared to that, the extra meter that goes from the surface of the Earth to the center of you isn't going to make much difference. And so the radius of the Earth will give us a perfectly reasonable value here. How's it going to look on the moon? Okay, for an object on the surface of the moon, the gravitational force exerted by the moon is G times the mass of the moon times the mass of the object over the radius of the moon squared. And that would be the object's weight on the moon. Again, the crucial details. The two objects are the moon and the object, so you have to have the mass of the moon and the mass of the object there. And the distance that matters here, the separation between the centers of the objects, is the moon's radius again. And the masses that matter, the mass of the moon and the mass of the object. So that's where weight comes from. Now let's consider some conceptual questions about gravity and the force of gravity and see how things turn out. At what point between the Earth and the Moon is the gravitational force on a spacecraft due to the Earth and the Moon closest to zero? Now, something important to learn about forces, they have direction. Okay, an example of two forces or forces having a direction is people having a tug of war with a great big piece of rope. One team is pulling one direction, the other team is pulling the opposite direction, and the forces they're exerting on that rope are in opposite directions. So, in this diagram, an object that's in between the Earth and the Moon will have the Earth pulling that object to the left and the Moon pulling that object to the right. Gravity doesn't vanish in space. In fact, it's what keeps the Moon in orbit around the Earth, is the gravitational force that the Earth exerts on the Moon. So it doesn't just disappear up there. Think about point A. Okay, that happens to be closer to the Earth, and the Earth already has a lot more mass than the Moon. In fact, the mass of the Earth is about 85 times the mass of the Moon, somewhere in that neighborhood. And so if you're closer to the Earth wins because gravity gets weaker with distance, and you're closest to the thing that has the most mass, so it's going to exert a much larger force. Similarly, if you go exactly halfway between the two, the thing that has the most mass is going to win again. So if you're at point C, the Earth is going to be pulling harder on you, 85 times harder than the Moon is, because the distance part of the equation isn't going to show up in here, or it's equal for the two masses that are pulling in opposite directions. But in that case, if you're equidistant between the two, the one that has the larger mass is going to be the one that wins the tug-of-war. I didn't even mention B, but it's closer to the Earth, which is the more massive thing, and so the Earth would be pulling harder at point B. The closest place where it might be zero would be point D. It's closer to the Moon, and so if you were just considering the distance part, the Moon would be exerting quite a bit of a larger force. The force gets weaker with the square of the distance, and that distance is much farther from the Earth, so it'll be much weaker. But it also depends on the mass of the object doing the pulling, and Earth would be doing the pulling. It's got 85 times the mass of the Moon, so point D is actually about where the force of the two things, Moon pulling to the right and the Earth pulling to the left, would be about the same. Now here's an interesting one. At what point on the diagram will the gravitational force be less than a fourth of what it is on the Earth's surface? So point A, it's about 20 miles above the surface, and that's above about 99% of the Earth's atmosphere. Point B is about 250 miles above the surface, and that's about where the International Space Station orbits. Point C is about 350 miles above the surface and is about where the Hubble Space Telescope orbits. You may not be aware of this, but there were servicing missions by the Space Shuttle up to the Hubble Space Telescope, I think 3 of them, that did things like improved the optics, replaced parts that were either worn out or that could be improved with some new technology and stuff like that. On the last servicing mission, the pilot of the Space Shuttle was a graduate of Big Bend Community College and someone who had gone through the flight program at Big Bend. So here are the choices. A, the gravitational force at point A is less than a fourth of what it is on the Earth's surface. B, the gravitational force at point B is less than a fourth of what it is on the Earth's surface. C, the gravitational force at C is less than a fourth. And then D is the gravitational force at A, B, and C is less than a fourth of what it is on the Earth's surface. And E, at none of these points is the gravitational force less than 1/4 of what it is on the Earth's surface. And I'm not going to answer this here. I'm going to let you maybe think about this. You could pause the playback if you want and think hard about it, and maybe ask in class what the correct answer is. This is a place to do calculations. And then here is a ranking task. I want you to compare your weight on each of these planets, from which planet is heaviest to which planet is lightest, and rank the planets in order according to what your weight would be on those planets, from the heaviest planet, where you would be the heaviest, to where you would be the lightest. And you might want to pause the playback here and just think about that. All right, what about orbits? How do you put something into orbit? The trick is you have to make your satellite move sideways really fast. Okay, remember Earth's orbital speed around the sun? It's about 30,000 meters per second. That's 30 kilometers per second. It's more than 20 miles per second. That's how fast we have to go to not go spiraling into the sun. We managed to have a pretty stable orbit maintaining a speed like that. And that's a situation where we're orbiting the sun. But what if you want to put something into Earth orbit? Okay, well, the trick is you have to make it move sideways fast, but you also have to get it above the atmosphere. On February 1st, 2003, the Space Shuttle Columbia, which had been in orbit, re-entered the Earth's atmosphere. Usually the space shuttles would use the Earth's atmosphere to slow them down, but they got very hot while they were doing that, and the leading face of the space shuttle, including the leading edges of the wings, had these bricks on them, ceramic bricks that were made of something that was similar to Corning ware. I don't know if you've ever used that white ceramic stuff. Heat doesn't transfer through that very well, and that was the whole point of these bricks that were a few inches thick on the front leading edges of the space shuttle and the nose of the space shuttle. And they would get very hot on re-entry, but they were designed in such a way that by the time the space shuttle finally got down to where it was moving slowly and could radiate that energy away, that heat would not have gotten through the tiles. But on that particular mission, some of the tiles had been damaged by a piece of insulation that fell off a booster rocket. One of the wings didn't have a complete coating of that stuff, and that wing got heated up during re-entry and basically buckled or came off the space shuttle. It lost all aerodynamic ability at that point and just sort of blew apart in the air over Texas, and pieces of debris were spread all over Texas and Arkansas and other places in the southeast there. And all the crew members died in that disaster. So you need, if you're going to be going fast enough to orbit, you have to get above the atmosphere. The Hubble Space Telescope, which is in low Earth orbit, 350 miles up or so, is going more than 17,000 miles an hour, and it has an orbital period of about 90 minutes. So what you have to do is first get above the Earth's atmosphere and then start tipping your rocket over sideways and get it going really fast so it stays up there. If it's not going fast enough, it'll spiral down into the atmosphere and burn up. So that's what you have to do. But the Hubble Space Telescope, 90-minute orbit. Now, here's some information. The International Space Station is a little lower than the Hubble Space Telescope. And this is some information for the 19th through the 29th of April 2018. It's a website called Heavens Above, where you can go and look up, find when the International Space Station will go over for your particular location. And if I find one on here, let's see, on the 19th of April, This is showing all of the flyovers, including the ones in daylight, which you can't see very well, if at all. If you knew where to look, you could, but there was one at 9:39 in the morning. Okay, and this gives the details of it, so if you wanted to spot it through a pair of binoculars or a telescope, you could do that. There was another one at 11:13, and so that would be, let's see, about 92 minutes later, I think. So yeah, about 90 minutes. And then there was another one at 12:50, which is about, what is that, 97 minutes later? I don't know. I'd have to think too hard to figure that out. But something like that. And if you go through the day, just about every 90 some minutes, there's another flyover of the thing. For a while, until you get to the one in the evening. And then the Earth is rotating underneath that orbiting International Space Station, and after a while, when it does the orbit, it's passing somewhere so far east or west of us that we're not going to be able to see it anymore. But then if you look at the next day, the 20th of April, first one is at 10:21, the next one is at 11:57, almost 11:58, and so that would be, oh, let's see, about 96 minutes apart there. So that's the case for artificial satellites anyway. Earth's moon is just another satellite, but it has a really big orbit. It's about 250,000 miles away, as opposed to these things that are only 250 or 300 miles above the Earth's surface. The Earth's moon only has to go about 2,300 miles an hour, with an orbital period of 27.3 days, and it doesn't have to go very fast because the gravity out where it is so much weaker that it doesn't have to go as fast to not be falling into the Earth. And the moon formed out there, and the stuff out there that coalesced to form the moon that wasn't going fast enough fell into the Earth and became part of the Earth. The stuff that was going faster may have just left the orbit of the Earth, gone away and become an asteroid somewhere. In between, you could have orbital periods of lots of different things. You could have an orbital period of, say, 24 hours. That would orbit the Earth in the same amount of time that the Earth takes to spin on its axis. If you happen to have a satellite dish in your yard, it's aimed at a satellite that has an orbital period that matches the rotation rate of the Earth. That's kind of interesting.